this slideshow actually is in addition to your reading in section 13.2 in your ebook, which discusses similarity mappings and similar triangles. So we discussed mappings in the last section, where each point corresponded with a single point in an image. We're going to have the same thing here, except we looked at congruence in the last section. We're going to look at similarity in the gone too far. Each point on the quadrilateral, as I said before, on the image is twice the distance as it is to the figure, original figure. So we call 2 the scale factor. Okay? And it turns out that if we have a scale factor that's bigger than 1, we'll get an enlargement of our figure. If it's between 0 and 1, we'll get a reduction of our figure. And if it's negative, the image is going to be inverted. So here we have a mapping of this smaller, crazy little figure onto another. Not all the points show all the corresponding points with them, like the points on the here and here. They're not all mapped. But we can see just from a few of these points that O to X, that distance, and this distance, the larger distance turns out to be 3 times the smaller distance. And that happens between every point on the image and its corresponding point on the figure. Okay? Also, what ends up happening is that this line segment CX will be a third of this line segment Z prime X prime. So the figure is 3 times larger as far as its length than the figure we started out with. Here's where we have the larger image A, B, C, D being mapped onto the smaller image. Okay, so if we wanted to figure out the scale factor here, this is 1/3 of the larger distance. So each of the side lengths, or this arc length, have been reduced by 1/3. So here's an instance where we have a negative scale factor. If I look at the distance from O to G and compare it from O to G prime, this is 1/2 the distance of that. But the projection point is in between the objects. Okay? So if I take into account the direction, the scale factor is a negative 1/2. The negative means it's been inverted. The exact way camera lenses, or cameras, and our eyes work. So sometime when you were taking health class somewhere, that you would have learned that when an image is projected on the back of your retina, it's always upside down. And then your brain turns it right side up. Well, that's exactly what happens right here, because you're looking at the person and the image. The light source, or the lens, that it's looking through is between the image here and the person. The same thing happens here. The lens is between the image and the person. So it's flipped upside down. And then the camera, if it's an old type camera, I'm not sure how new digital cameras work, but if it's on film before, it would be upside down. And then when it imprinted, it would be right side up. on your retina, the back of your retina is projected upside down, but then your brain flips the image right side up. Okay, so again, we have a similarity mapping, one figure to another. Okay, so what happens with our similarity mappings? The angle measures remain the same. Okay, so corresponding angles are congruent. So angle D here is congruent to D prime, E is congruent to E prime, and so forth. Okay. The lengths of the line segments all change by the same multiple, which is what I mentioned before. Okay. In the image, D prime, E prime is twice what DE is, because the scale factor is 2. So what we can say is that the ratios between corresponding side lengths are all equal to each other. In this case, they're all equal to 2. So similar polygons, this is a definition. 2 polygons are similar if and only if there's a mapping from one figure to another, such that the corresponding angles are stay congruent, and the lengths of the corresponding sides have the same ratio, or we can say the lengths are proportional. So if we want to check if 2 triangles are similar, we don't have to check both conditions, as long as if we can check with our information that all angles are congruent, then we know that the sides have to be proportional. Or if we can check that all the side lengths are proportional, we know that all the side lengths are congruent. But we have some properties, similarity properties, just like we did congruence properties. This is the angle-angle property, similarity, for similarity, and so all we have to know that if two angles in one triangle are congruent to 2 triangles in the second one, then we know that those similar triangles. Now we only have to know 2 of them, because the third angle will have to be congruent, because they all have to equal 180. So if I have that this, and this is not going to be pretty, you'll see a better picture of stuff like that here in a minute. If these 2 angles are congruent, and these 2 angles are congruent, then if I subtract that from 180, I'm going to get the same thing between here and here, and those are going to be congruent also. So I don't have to know that all 3 angles are congruent. It's enough to know that 2, if I'm dealing with a triangle. If it's anything else, then I'll have to check to make sure all the angles are congruent. Okay, there's also a similar property, side, side, side. So it's kind of analogous to the side, side, side congruence property, except this says that if the corresponding sides of 2 triangles are proportional, that means if you set up the ratio between corresponding sides that they're equal, then the 2 triangles are similar. And there are examples in your book of this working. You can also say that their scale factors. That scale factor has to be the same. If you check their ratios, it all has to be the scale factor. Okay? Now, if you have a scale factor of 2 between 2 similar figures, okay, the area is going to be the square of their scale factor, because you've increased in 2 directions. You've multiplied by, so if your scale factor is 2, you're multiplying on 2 by this direction and by this direction. So the area is multiplied by 4. To get the area of the new figure. If you're looking at the volume, you're multiplying in 3 directions. Okay, I'm sorry, let's go back to this one. If we're looking at the surface area here. So again, surface area is just another measure of area. So you're increasing in 2 directions, length and width, or maybe just only length and height, but it's still only in 2 directions. So again, it's also k squared, the square of the scale factor. The volume is increased by the cube of the scale factor. So we can use similar figures to measure indirectly. Like, I don't have, this person standing next to this building doesn't have a yardstick to measure all the way to the top of the building. So what she does, she's an architect, she goes out and she places a mirror on the ground right here. Okay? And she stands back until she can just see the top of the building in the mirror. Okay? And it turns out that when she's this way, these 2 angles are congruent. So, and that's a property that says the angle of incidence is equal to the angle of reflection when you're reflecting light. So when she looks up, she's looking up, she just sees the top of the building, then she's at the same angle. When she's looking down is the same angle that the light's being reflected at. And she's standing up straight, and so is the building. So we have 2 right triangles, and they're similar because of AA, similarity property. And I apologize if you hear a roar behind us. Well, someone has turned a machine on that's very loud. So now, since I know that these 2 triangles are similar, I can set up some proportions. Well, her height would correspond to the height of the building, so I don't know what that is. I'll call it X. So her height to the height of the building has to be the same as her distance from the mirror compared to the distance of the building from the mirror. So now all we have to do is cross multiply and divide. So my pen, I'm not sure that it is working. So we take 6 times 25 is equal to 3x. So we have 150 is equal to 3x. Divide both sides by 3. X is equal to 50. So this building is 50 foot tall.